So the skins are attached to stringers and frames. So they're either bonded or riveted to the stringers and the frames, and that's what gives us the tube, okay, in which we can pressurize for flight. We can pressurize it because we have an aft pressure bulkhead and a forward pressure bulkhead, and this is one solid tube that can be pressurized. Okay, and we pressurized it in what is described in a semi-monocoque structure. Okay, a semi-monocoque structure, which is skins on top of stringers and frames. Other reference, well, the stringers are referenced. Okay, they're attached to the frames. And they're in terms of location, so that we can, let's say, for SRM purposes, describe the location on a skin. The 12 o'clock position is S1. Okay, and then we go left or right. So 2L, 3L, 4L, up to 27L, or 2R, 3R, 4R, up to 27R. Okay, for the number of the stringer we are referring to in our damage report. You can also see in this diagram that at 17R and 17L is the actual reference for the floor beam. And some pictures from the factory. So this is the forward pressure bulkhead. So if you open the radome, this is what you would see. And this inside, where you'd see the floor beam, the frames, and the stringers, and the skin that attaches to all of that. The 900 NG has the Dash 900 can have a flat pressure bulkhead. Okay, this is a customer option. This enables the aft galley to be pushed up flat against the flatness of the pressure bulkhead and give a little bit more interior space in the cabin. Okay, as I said, it's a customer option. I don't know if they do one-offs. You probably have to order 50 aircraft before Boeing entertain that option. I don't know. Most of the material in the wing is aluminium. So what's attached to the wing structure is the engine nacelle and pylon, the flight control surfaces, ailerons and stuff, the main landing gear on the underside, and the wing tip or winglet. From the underside, looks like this. This will be the left-hand wing. So from the underside, you can see the engine, can't see the strut or the pylon. And you can see all these access panels for the tanks. So you've done the top and the bottom of the wing. And inside the wing, it's got spars and ribs. Got a front spar. It's got a rear spar. And the front spar transmits most of the load. Yeah, when the aircraft's doing its forward motion at 900 kilometers an hour, that's the front spar that bears the massive load onto it. It's also a mounting structure for the leading edge flaps and slats. So this is where we attach the flaps and slats onto the front spar of the wing. The rear spar transmits loads to the fuselage. And it's also the mounting structure for the flaps and the ailerons. Okay, and don't forget, inside is a fuel tank. All of this will be fuel, remember? This is what it looks like in the factory. They're assembled in vertical jigs as they are like that. And the spars and ribs are then connected first, and then the skins are attached later on. The winglets are made of graphite spars, aluminium ribs, and aluminium skins. Okay, there are forward, aft position, and strobe lights included into the structure. Okay, when the original NGs came out, they came without winglets. Okay, they made about 2030. And then they decided, oh, we'll put these winglets on. So the first 2030 had to go and get remodded and get winglets because they were without winglets. And then they modified the production line so that all subsequent NGs came out with winglets from the factory. The nacelle is the fairings and the components that surround the engine. The nacelle gives an aerodynamically smooth surface to the strut and the engines. It contains the inlet cowl, this one here, the fan cowls, left and right, the fan duct cowl and thrust reverser, left and right, the primary exhaust nozzle, and the exhaust plug. The pylon is the strut that attaches the engine to the wing. Okay. The strut contains fuel lines, electrical harnesses, hydraulic lines, pneumatic ducts, fairings, and fire overheat detector extinguishing lines. The horizontal stabilizers have spars and ribs. The elevators have graphite composite materials. The vertical stabilizer is made from aluminium. The rudder is a graphite composite, and we already mentioned the dorsal fin. This is pure fiberglass. So inside the main torque box, they call it, of the vertical stabilizer, they're made of carbon fiber reinforced plastic, and we got the spars, the ribs, the stringers, and the skins. Auxiliary structure is made from aluminium or titanium. The leading edge and tip are removable. All the panels are fiberglass. The rudder and tab structure is carbon fiber reinforced plastic. So the 737 should, or all aircraft should have an aerodynamically clean shape and smooth exterior surface to give high performance. Damage that's not repaired, dents that are not filled, or repairs that change the shape of the surface decrease the airplane performance. We keep the initial contour and smoothness of the airplane surfaces as intact for as long as possible to be able to keep up that fuel efficiency and the aircraft longevity, so to speak. Therefore, if we do have damage, we have 3 categories of aerodynamic smoothness that could be affected. And these are the critical areas, the extra critical areas, the critical areas, and the non-critical areas. So depending on what area you have your damage, there will be different SRM limits for the different categories of smoothness criticality, aerodynamic smoothness. Okay, stands to reason. Just as an example, we put the critical areas. Okay, the critical areas here, because of skin smoothness, aerodynamic waviness, they call it. Okay, these areas have to be free of any cause or variation of the air passing them, because these instruments, the pitot-static stuff, can be affected with the readings if the air is distorted because of a big dent in the area. Therefore, these areas around these pedostatic probes and ports are considered critical areas, high, what do they call it? Extra critical areas. And of course, in the SRM, we classify the damage. We classify damage just like any other SRM in terms of if it's in the pressurized area first or the non-pressurized area, then you have different SRM provisos. Then you have to describe what the damage is. Is it a crack, a scratch, a gouge, a nick? Is it corrosion? Is it a dent? And for each of these damages, there'll be an SRM extract within the limits of that crack, scratch, gouge, nick, corrosion, or dent. And that's how it works. So the SRM will direct you to perform the work after the structural damage is found. Okay, and here you have your ATA chapters. Oh, no, you don't. You have chapter numbers 52. That's a bit confusing because it's all 52. 52 is doors. Maybe in the SRM, chapter 52. I'm not sure. But this is the training document. Could be wrong before we know. But what we definitely know is that for each damage, you check the ID pages 1 to 99 to locate the area. When you found the area, you check if the damage is within the allowable limits or not. If it is, then you protect it and fly on. You make an MEL for it within however many flight cycles or hours the SRM will specify. If it's not within the limit, is there a specific repair in the SRM? Yes, then repair it in accordance with that SRM and release the aircraft. If there is not a specific repair, in other words, you're the first person ever to have had this damage on 20,000 737s ever built, then there should be examples in 51 of repairs that apply. Then use one of those examples and repair the aircraft and release it. If there is nothing similar to what damage you have, you're going to have to contact Boeing and they will draw up a new repair for you. Okay. That's how it works. Now we talked about skin waviness, and the skin waviness really does affect aerodynamic smoothness. Okay, so we have to avoid that in critical areas of the aeroplane's skin. Okay, and the limits are, there is a coefficient where you has to be, depending on the depth of the dent, it has to be, I don't know, 15, 20, 25 times. The length has to be 25 times the depth. Okay, or whatever the SRM quotes, depending on where the location of this dent is, what criticality of smoothness, aerodynamic smoothness it falls within. Then you have to have the amount of concaveness, if it's an indentation, that's allowable according to the SRM. It also has guidelines for the amount of material that can be removed from a damaged surface. Okay, so if you have, for example, there's been a gouge or a nick or something, and the SRM will tell you to remove the material, smoothen it out, and then once you've smoothened it out, measure it again. Okay, so the SRM will give you specific allowable or specific guidelines. So here you see we've got a let's say it's a nick or a dent, and in order to measure it, we have to find its deepest point. Well, we measure it the deepest point, and then we have to blend it out so that it meets the 20 times depth criteria. Okay, in the skin repairs, there are recommended skin repairs in Boeing, and there are also three main types of skin repairs to restore the load carrying capability on the fuselage. The three main skin repairs are an external rough repair. So you can see here the mush heads, the rivets are actually protruding. Okay, this does not offer very much aerodynamic smoothness. Okay, then you have an external clean repair. Sorry, this one, an external clean repair where you've you got the rivets you're using are flush. Okay, but it's a skin external to the aircraft skin. You just smoothing it out. Okay, and the flush repair means that it's as good as the original one. Okay, a clean repair where the rivets are flush with the skin. Okay, and you wouldn't notice the difference. Okay, if they're not designed properly, fuselage repairs can increase drag and fuel consumption. And you say, well, how much fuel consumption can it be? Well, even if it's 0.5%, 0.1%, if it spends the next 20 years consuming 0.1% more fuel than it should be, it could amount to a lot of fuel. When we're removing damage, okay, so this is for composites now. We put the repair ply at the boundary for that ply. Okay, you taper sand it and help fill the ply boundary. It's necessary to make a template of each ply in the repair. Okay, so these plies, don't know if you've ever seen composites, how they do it. They put one layer, it will be in the fore and aft. Then they'll put another layer, it'll be 45 degrees. The fibers we're talking will be at a 45-degree angle. Then another layer will be 90 degrees. Then another layer will be another 45 degrees. So if you've dented it or punctured it, yeah, you have to take out all of these layers. And then the new layers you're going to put in, you have to put them in the same orientation as the original, because that is what gives it the rigidity, all these different layers at different angles. Okay, so you can't just fill it in with glue. You have to do a proper repair, layer for layer in the right plane. So most repairs require a taper ratio of 1/2 inch per ply. Okay, so depending on how many layers you take out, all right, you need to taper them off at around about 1/2 inch a ply. Some tapers require a 30-to-1 taper ratio for laminate with 6 or more plies, and a 50-to-1 ratio, okay, or laminates with fewer than 6 plies. All right. And a good taper is required for correct load transfer between the repair and the original material. If the taper is wavy or gouged, yeah, the load transfer will be uneven and could cause the repair to fail. And if the repair fails, you'll probably get what they call delamination. Once it delaminates 1 micrometer. The first thing that will happen is at 35,000 feet, water will get in there. Once water gets in there, every time it goes to 35,000 feet, that water will turn to ice. That ice will then freeze. Well, that water will then ice and will expand and then make the little hole into a crack. And the crack will get bigger and bigger, and the delamination will get bigger and bigger. Therefore, the repair is critical. It's so critical that it's done by making sure that the bond is absolute, by removing by vacuum all of the air that could occur between the plies. Okay? And that's how you do it. You use a bagging film, a breather ply, and a parting film to make the repair. You seal the vacuum bag on the repair. Okay? Then hold the vacuum for the time shown in the SRM. It will tell you for 12 hours, 24 hours, however long it says. Okay, this will compress the plies and will remove the air and the moisture from the repair so that you don't get any damage further down the line. And finishes, all right, how you protect all of this, be it a metallic part or a carbon fiber part or a fiberglass part. Finishes to protect the composite. Oh, this is not a metallic. For composite parts. Okay, parts on different areas of the aeroplane have different design and environmental conditions. For example, the radome, which would be fiberglass, has to be fiberglass because behind it is the weather radar that has to emit high power pulses, a voltage at high power. Now, the paint you're going to use on it also has to be of a material that allows the voltage or the signal to be transmitted through that. So it's there is specific requirements on what the finish should be, okay, when you've actually made the repair. Speaking of the radomes, okay, certain areas need a rain and erosion protection. Okay, so I'll never forget, if any of you were involved in storage maintenance during COVID, there was a requirement for 737s to put this corrosion preventative material on all the leading edge slats, on the inlet cowls, okay, on all the metallic parts to preserve the aircraft because it was in storage maintenance. Okay, we don't do that as a matter of course. When the aircraft's in day-to-day operation, we don't do that. But if the aircraft is in storage or is sitting for a certain amount of time, the AMM will prescribe limits on how long it can stand without any maintenance. And if it's longer than a prescribed limit, you have to do storage maintenance, which is erosion protection. Okay. So areas that require erosion protection, the nose, the radome, the wing leading edges, slats, the horizontal stabilizer, leading edge, the vertical stabilizer and the HF antenna, and the engine inlet cowls.